Hi guys. So by the time you watch this video, you'll have test number 2 behind you, so that's great. And then this video, this activity is your first introduction to quadratics. So we've talked about linear functions, exponential, and then this chapter is going to focus on quadratics. So by the end of this activity, you'll have an idea of what quadratics look like on a graph, and how if you change certain parts of the equation, what that does for changing in the graph. So we're starting off with a situation where you take and you just release a ball. You're not throwing it up, you're just dropping it from the roof of a tower. Okay, and they're giving us the function right here that represents the height for time. So if I want to figure out how high it is after 1 second, I plug in t equals 1, 2 seconds, t equals 2. And you notice you have a negative 16 in front. That shows that the ball is dropping. Okay, so they want to first, we're just going to sketch a diagram of the path of the ball. So we've got some tower here that is 1,450 feet high. The ball's starting up here, and you're just dropping it straight down, okay? If I were throwing it up and then falling down, it would just be a little bit different picture, but this one I'm really just sticking out my hand and dropping it. Okay, so I'm already filling out this table. I did it ahead of time, so you should stop in the video and use the function right here and fill out this table of t equals 0 through 10 seconds to figure out the height for the first 10 seconds of this ball. Okay, so once you do that, come back here and give your table a check with mine. And then we can go on from that and figure out what are some important points of this graph. So the next thing we're going to find out for this is how far does the ball fall during the first second. Okay, so if I'm talking about from 0 to 1 seconds, I'm going to subtract the two y values. So after 1 second, it is, well, at the beginning it's 1450 right at the top of the tower. After 1 second, it's at a height of 1434 feet. So that's a difference of 16 feet that it's fallen. Oops, let me fix that. That should be feet, but I was saying falling at the same time. Okay, so this is feet. Okay, keep in mind that that's what it fell. So what about from 1 to 3 seconds? Okay, well, at 1 second, the ball is still 1,434 feet high. And then it's dropped to 1,306. These are just using our table from the page before. So then it dropped 128 feet from there. So let's look at this. We just found this rate of change, really. From the rate of change between 0 and 1, the rate of change would actually be negative 16, okay, because it dropped. From 1 to 3, keep in mind this B right here is the same thing we were finding for C right there. So what is the rate of change from 1 to 3 seconds? Well, it dropped 128 feet per second. Let me add that over here. Feet per second. So when I look at that, oh, actually that's not right. Let's fix that, because really what should it be? This was 128 feet per, let me erase that, per 2 seconds, right? Yeah, sorry. So if I actually divide that out, that would be negative 64, sorry about that, feet per 1 second. Okay, so the reason I caught that and why I wanted to fix it was because if we want to compare these and see what kind of relationship it is, they have to be both the same unit. So they both have to be feet per second. So when I look at this, between 0 and 1, it dropped 16 feet per second. But then between 1 and 3, it dropped 64 feet per second. So when I look at this, they're asking us, could this possibly be linear? And we would say no, because if it was linear, that rate of change would have come out to be the same all the time. So there's not a constant rate of change. In order for it to be linear, that would have to come out to be the same for any amount of feet. for any amount of feet per second on the entire table. What is the value of h when the baseball strikes the ground? Use the table. So if we go back to look at the table, when does it hit the ground? We're not sure exactly. We're estimating it. So we're going to say, for this would be when h equals 0 for it to hit the ground. And that happens between 9 and 10 seconds. By the end of this chapter, you'll be able to find that by hand. Okay, so what is a practical domain of the height? Okay, of this function, the practical domain, well, let's just estimate because we're not sure where this is going to hit the ground. We're just going to say, just so we can use this number, we'll say about 9.5 seconds. So practical domain of this, all the x values, or really this is values for time, our time really should be between 0 and 9.5 seconds. I'm using interval notation there. If we want to use inequality, we'll say here. I just picked 9.5 so we could actually use this value in our domain. That's practical. That's how long this ball is in the air. So what's the practical range? Well, the range is my height. It's never going to go above that initial height that it had, and it's never going to go below ground. So we would say 0 to that 1450, which was the initial height. Again, I'll put it in the other one if we want that too. Okay, so again, I would stop the video right now and do part D, because part D takes a little bit of time to figure out what units you should use, label everything, and then plot your points. But plot all those points from that table we just made. And then once you have it, come back to the video and check your graph with what I have right there. So at first glance it could look linear, but we're going to realize that the quadratic is a better fit for this. Okay, and then part E is the graph of the height, the actual path. So remember, at the very beginning we started with drawing the path. This is not the path of the ball. This represents the height versus time. It's not the actual path. Okay. So now let's take a look at what this looks like, the entire graph on the calculator. So you're going to want to put this into Y1, and they're giving you right here some windows that they want you to use, okay, so that you can see everything we want to see. And think about what we just graphed was really like this part. We only graphed what was practical, but we're looking at the entire thing now as if this didn't have anything to do with dropping a ball and keeping height and time positive. So describe the important features of this. So let's put a couple things down that we think are important about this graph. Okay, one thing is that it's not a line. This is what we call a parabola. Oops. Opening, what we say down, is opening upside down. It's opening like this rather than like a U. Okay, there's one important thing. Another thing is it has a y-intercept of 0, 1450. Another important thing is this one is symmetric. They're not all like that. Well, they have some symmetry, but not always about the y-axis. Symmetric about y-axis. This one happens to be. And one other thing, if you go on the calculator and find those x-intercepts, you'll find the exact ones. And these come out to be, we had estimated 9.5 before, but plus and minus 9.2. If you actually find this point right here and this point right here, using either the table or the go into calc and do the actual 0, you'll find that, or actually it's 9.52, sorry about that. Find the exact ones. Okay, so we actually had a pretty good estimate before. So the x-intercepts for every quadratic are not always plus or minus, but it can always potentially have 2 because of the shape. So here is that, now we're kind of describing what we just came up with. So a parabola, a graph of any quadratic. So remember, let's go look in this definition here. A quadratic is anything that can be written in that form. Okay, we've got three different terms, but they don't always all show up. The important one to show up here in this equation is right here, because if we didn't have that one, we wouldn't have an x squared, and then it would be linear. So you notice in here that a can't be 0, because if a is 0, then this is not quadratic anymore. But b and c sometimes are 0, and if you look at our function with the height, there is no linear term. This is what we call our linear term, because it's x to the first, and this is our constant term. And they're not in every single one. Okay, so what we're doing down here is identifying what a, b, and c are for each of these. So if we have a quadratic y equals 3x squared, our leading term is 3. This does not have a linear term and doesn't have a constant. Whereas the next one, the leading term, the quadratic term is -2. There is no linear term, constant, there's a 3. The next one over, we have quadratic term of 1, linear term coefficient is 2, and our constant's -1. And then the last one, remember, well, I'll get to that in 1 second, but the next one, our quadratic term is -1, our linear term is 4, and no constant. So what I would suggest doing, we're going to do it again later on in this activity, but I would go on the calculator and graph these and just kind of look at the similarities, okay? One thing to keep in mind when it's in this form, this constant term is always our y-intercept. It's kind of just like being in mx plus b form. That last term without a variable is our y-intercept. So that can tell us a lot about the graph. And I want you to start realizing what a tells us about the graph. B is a little bit trickier to kind of come up with a pattern, but A and C can really give us a good idea of what this is going to look like, just a sketch.